things we will discuss today, first we will explain what is partitioning cluster analysis. Then we will move on to the first type or first method of doing partitioning clustering analysis, which is the K-means clustering. And within that, we will talk a little bit about something called the Lloyd's algorithm, which is the actual way to implement the K-means clustering. Then we will talk about the K-Medoids clustering. We will discuss how to select K. And finally, we will solve a manual example to show how the K-means clustering works. So without further ado, let's go into partitioning cluster analysis. So in partitioning clustering analysis, what we're trying to do is to partition our data set into K non-overlapping clusters. So K is the number of clusters, and we're trying to kind of partition our data set based on a specific criteria into these clusters. It's different from the hierarchical clustering that we discussed in last episode by the fact that we know K in advance. So in the hierarchical clustering, we don't know K in advance. We actually generate the full spectrum of number of clusters. But here we are focusing on a specific number. What if our data is clustered in 2 or 3 or 4 clusters? So basically, if we have a two-dimensional data as shown in this plot or figure, we can specify how many clusters we want. Of course, it's important to understand that we don't know the distribution that generated this data. So for example, if it's a multivariate distribution that have 3 different types, it could be 3 clusters, but we don't know this in advance. So what we are trying to do is just look at the observations themselves, just the covariates and how do they look like on the space, and try to generate clustering that is meaningful out of them. So let's say we look at the data and we think that they can be split into 2 clusters. So we specify our K to be 2, and then it will have 2 clusters such as this one, for example. If we decide that K is 3, it will be split into 3 non-overlapping clusters. If we decide that K equal 4, it will again be split to 4 non-overlapping clusters. So this is the idea. We specify a K and then we split the space or partition the space into these K clusters. So now let's go into the first method, which is the K-means clustering. As mentioned, all partitioning clustering start with specifying the number of clusters K. And then what we are trying to do is to assign all the observations in our data set to these clusters based on a criteria. The criteria is a loss function that we are trying to minimize, because as in statistical problems, we usually try to minimize a loss function to make sure that we achieve the optimal solution. So the loss function that we are trying to minimize in K-means clustering is called the total within cluster variation. And if you think about it just by the name of that loss function, it's calculating the variation within every cluster. So it's trying to create concise clusters that have minimal variation within themselves and giving you the optimal solution based on the minimum variation achieved by splitting the data into these clusters. So to understand the total within cluster variation, we first need to understand the within cluster variation. So the variation within a cluster itself is calculated, and then we sum that variation over all the clusters that we have to get the total within cluster variation. And when we minimize this, or we find the minimum value of this variation, it is our optimal solution for the K-means clustering. So basically, the within cluster variation, so within a cluster CK, we're basically summing the squared Euclidean distance of each point in that cluster from the center of the cluster. And if we basically open up this equation, it will come up to be like this. And basically, xi here is the observation in cluster CK. The xck is the average of all the points in the cluster. So let's say our cluster has 5 points. We're going to average all of these, and this will be x bar ck. And ck, between the modulus, basically is the number of observations in cluster ck. And the de xi, xj squared is the squared Euclidean distance. Of course, we can use any distance metric and it would work the same. It's the idea just that we're calculating the distance from the center of every cluster and squaring that distance to get a good idea of the within cluster variation. So once we sum this over the number of clusters we have, so that's same within cluster variation, we sum it from k equal 1 to capital K, and we're summing the variation for all the clusters. Now think about something. If we are talking about 3 or 4 clusters and 1000 data points, now we are supposed to look at every possible combination or partitioning of these 1000 points into these 4 clusters. So if you think about it, this will be too many possible partitioning, because every single point have a chance to be in any of the clusters, and then the second point can be in any of the clusters, and the third point can be in any of the clusters. So this number becomes a huge number of partitions, which is actually computationally impossible, even with the powerful computing that we have right now. In fact, if you only have 100 observations, which is very low for a big data or a machine learning problem, and only 5 clusters, you would be looking at 10 to the 68 possible partitionings. So in theory, K-means clustering is almost impossible to do. So do we just stop? Do we just say that K-means clustering cannot be done because the theory is too computationally expensive or even impossible to implement? Well, no. The Lloyd's algorithm comes to rescue. So the Lloyd's algorithm is a way to estimate the K-means clustering, and it's very powerful and useful, and it's computationally not complex to do or not expensive to do. So it requires much less number of computations. So the Lloyd algorithm starts by specifying K, the number of clusters, and then randomly selecting K observations from my data set to be the centers of the first clusters or the initial clusters. So they will be my initial centroids. So let's say I'm using K equal 3 and I have 1000 data points. I'm going to randomly select 3 points from those 1000 to be the centers or the initial centers of the clusters. Then I'm going to start assigning every single one of the 1000 points to these clusters based on their distance from those cluster centroids. So basically, if I selected point 1, point 2, point 3 to be the centroids of the 3 clusters, I'm going to calculate the distance from point 1 to every other point, and then from point 2 to every other point, then from point 3 to every other point, and I'm going to assign every point to the cluster that is closest to it. Then after my assignment is done for the 1000 data points, I'm going to compute my new centroids again by averaging the points that are within the cluster. So I ended up with 3 clusters. I'm going to go to the first cluster, look at probably 300, 400 points, take their average and say this is my new centroid. Do the same for the second cluster. Do the same for the third cluster. Then I'm going to repeat number 3, assigning the observations again to their clusters. And I'm going to repeat number 4 and compute the new averages or the new centroids. Then I'm going to do 3 again, do 4 again, until convergence. And convergence happens when the clusters do not change anymore, or the centroids stay the same for 1 or 2 or 3 iterations in a row. So here I reached my convergence and my algorithm will stop. Of course, if you didn't reach convergence, you will specify how many iterations as a maximum number of iterations you are willing to take until reaching your optimal clustering. Here we selected K number of points initially randomly. So this tells us, of course, you remember there are too many possible partitionings and we're not testing all of them. So selecting K in the beginning is going to probably affect our clustering based on that K that we have chosen. So usually in practice, we actually do a few random starts, and this is done easily in R by just adding an argument to the K-means function. So we don't start by only one random selection, because this is going to affect how my clustering ends, especially in more complex clustering problems. Now it's a good time to move to the second type of the partitioning clustering, which is the K-Medoids clustering. It's basically almost exactly the same. We specify the number of K. We randomly select K observations to be the initial medoids, which are the same as the centroid, but it's just because we are talking about a different algorithm. We're going to assign the observations to its closest medoid. But now here's the difference. Instead of computing the new centroids as the average of all points, we're actually going to select one of the points that are in the cluster to be the new medoid. So before, the average of the points could have been a new point in space that is not actually an observation. But now every new medoid has to be a point from our data that are within that cluster. And this is done by minimizing a function called the cost configuration. And I'm going to repeat step 3 and 4 again until I reach convergence. So the main difference is in step 4. And the cost configuration is basically the distance from for every point in the cluster to every other point, and summing all of these. And then I'm going to check what is the point that has the minimum distance from all the points. So let's say I have 5 points. I'm going to start by point 1 and calculating the distance from 1 to 2, 1 to 3, 1 to 4, 1 to 5, and summing them. Do the same for 2, do the same for 3, do the same for 4, and do the same for 5. And I'm going to end up with one of these observations, 1, 2, 3, or 4, or 5, that have the smallest sum of distances from the other points. And this is going to be my new medoid. And I'm going to repeat step 3 by assigning the points again to their clusters, and then computing the new medoids again. And this is, in a nutshell, this is K-Medoid clustering. Now let's talk about selecting K. So we say in every one of those algorithms in partitioning clustering, we started by selecting a K value. So how do we actually select the K value? In some problems, it could be intuitive because we have an idea of how many clusters we want to end up with. For example, if we are clustering a customers group, let's say we want to create 3 types of clusters: customers that are very loyal, customers that are probably gonna leave, and customers that are in between. So we want the K equal 3. But in many real life problems, we don't know what is K. So we use kind of 2 methods to specify K in the partitioning clustering analysis. The first method is called the elbow plot. So for the elbow plot, for every value of K, I'm gonna have a total within cluster variation associated with it. So let's say I start with K equal 1. I'm going to calculate the total within cluster variation, like the ones the equation we showed in the K-means slide. For K equal 2, I'm going to check what is the total within cluster variation. And for the range I'm satisfied with, so let's say I want to check for 5 or for 6 clusters, I'm going to check every total within cluster variation for every value of K. And I'm going to end up with a plot that looks like this. So let's say, for example, for K equal 1, this is my total within cluster variation. For K equal 2, it dropped. For K equal 3, it dropped sharply. Then for K equal 4, then for K equal 5, and then for K equal 6. So you might be asking, why don't I just go with the least? Because if you remember, I'm trying to minimize the total within cluster variation. But remember, if I end up with more clusters than I need, I probably can go to a point where K equals the number of observations, and my clustering will not be useful. The idea of clustering is to get the data into a few groups that make sense. So the elbow plot tells me that whenever I have a sharp decrease, I create an elbow, and this should be my optimal number of clusters. So in this case, the elbow was on K equal 3. So I should try K equal 3 as my number of clusters. Now the other way to select the number of clusters is more more numeric or mathematical, which is a measure of how similar every observation is to other observation within its clusters compared to observations in other clusters. So I'm measuring cohesion versus separation. So basically, this is gonna result for every single point, it's gonna result in a value that is ranged from -1 to 1, where 1 means perfect fit to this cluster, and -1, it means that it's perfectly fitting with another cluster. So I'll usually end up with values in between -1 and 1. And the higher the value of the silhouette statistic, the better this observation fits in that cluster. So if I take all the silhouette values for all the observations and their range, or basically their average, is somewhere near 1, it means my clustering is good. To demonstrate this, I'm not going to show how to calculate it because it's numerically complex to calculate, and we'll show it in R in another episode. But I'm going to use the scikit over here. They have a great example for it. I'm going to quickly explain how to look at the silhouette plot, which is a plot of the silhouette statistic. So if we look at this data, so it's clustered into 2 clusters. So the silhouette plot will look like this. It will have two clusters, each one is represented in a different color. And if you notice here, the range of the values is from 0 to 1, which means I don't have negatives, which means that my clustering is good. And the average silhouette statistic for the full clustering is around 0.7. And this is a good value. And as you notice here, it looks like the clustering is good. If we go to a more complex example, so let's look at, for example, this clustering. And if you notice 2 and 5, they have points that are close to each other. So if you notice here, we have some observations. So every small line here, horizontal line, is an observation. So we have observations with negative values, which means that they don't fit within their clusters very well. But the overall average is around 0.45, which also means our clustering is good enough. So if I'm looking at multiple values of k, I'm going to select k, the number of clusters that gives me the highest silhouette statistic value. Now let's move into an example. So we're going to do an example on K-means, and you can do it on K-Medoids, except that K-Medoids is going to be a little more expensive in calculation wise to get the Medoid every single time. But as I mentioned, you just calculate the distance from every point to all other points in the clusters. Then you choose the one with the smallest distance as the new Medoid and repeat the process. So to make our lives easier, we're going to look at one-dimensional data. And the only difference that's going to happen when you do it with 2 dimensions or 3 dimensions is calculating the distance. So the distance here is going to be just subtracting 2 numbers, whereas if you're doing it with multi-dimension, you will use the formula for the Euclidean distance or for whatever distance metric you are using. So this basically is how our data looks in the number line, because it's a single dimension, only x1. So we have a point here, 100, a point here, a point here, a point here, a point there. So first we're going to select k. So let's say arbitrarily we want to select k equal 2. We believe that 2 is a good number for our observations. Now we need to select initial centroids. So let's say we just randomly want to select the first 2 points here as the initial centroids. So observation 1 and observation 4. Let's color them to make it easier to visualize the clustering. So we will have a cluster, our initial clusters will be 1 and 4, and then we're going to assign the observations to their closest centroids. So we're going to assign all of these to either 1 or 4 based on the closer one, and of course you can tell the closer one is 4, but imagine you have 100 data points, you will have to go through the calculation. And now you will compute the new centroids after you finish your assignment of these 6 observations, and you will repeat 3 and 4 until you converge. So let's go through the first iteration. So the observations are listed here, the x1 value is listed here. We're going to calculate the distance to cluster 1 and the distance to cluster 2. So as you remember, we started by point 1 being the cluster 1 centroid and point 4 being the cluster 2 centroid. So obviously the distance here and the distance here will be 0. But for the others, we will have to calculate the actual distance. So if point 1, observation 1 is at 100, and the center of cluster 2 is on 120, the distance is 20 because 120 minus 100 is 20. We will do the same for point 2. So point 2 is 150, so it's going to be 50 away from cluster 1, and it's going to be 30 away from cluster 2. For point 3, we're going to calculate the distance, so it's 75 from cluster 1, and it's 55 from cluster 2. For point number 4, it is 20 from cluster 1 and 0 from cluster 2. For point 5, it's going to be 80 and 60. For point 6, it's going to be 180. So we finished calculating the distances. Now let's do the assignment. So the assignment for every observation is going to be to its closest cluster. So point 1 obviously will still be in cluster 1. And obviously observation 4 will remain in its cluster because of the 0, and then observation 2 will be assigned to cluster 2 because it's closer than cluster 1, so we're going to color it in green. Observation 3 is going to be green as well. Observation 5 is going to be green because 60 is less than 80, and observation 6 is going to be green because 80 is less than 100. So this is how the new clustering looks like. And now I have to calculate the new centroids. And as we mentioned, the new centroid is going to be the average of all the points in the cluster. So for cluster 1, it's going to be 100 over 1, so it's going to remain as 100. And for cluster 2, I'm going to sum 120 plus 150 plus 175 plus 180 plus 200, and I'm going to divide it by 5. So I'm going to end up with 165, so the centroid of the cluster will be somewhere around here. And now I go into my second iteration, and I'm going to again calculate the distances, except this time for cluster 2, the centroid changed to 165. So for cluster 1, point 1 is at 0 distance from the cluster centroid. For point 2, the distance is 65. For observation 2, it's 50 away from cluster 1, and it's 15 away from cluster 2. For point number 3 or observation 3, it's 75 away from cluster 1, and it's 10 away from cluster 2, and so on. And then again, I'm going to select the clustering based on the point that is closest. So point 1 will be in cluster 1, point 2 will be in cluster 2, point 3 will be in cluster 2, point 4 will be in cluster 1, point 5 will be in cluster 2, and point 6 will be in cluster 2. So my new clustering will look like this. And again, I'm going to do step 4 and calculate the new centroids. So the new centroids will be point 100 plus 120 over 2. So cluster 1 will have a centroid at 110. And cluster 2's centroid will be 176.25, which is the average of all these points. Now I'm gonna again calculate the distances, and if you do them to practice, you will find that the distances are this, and you will assign the observations again based on the closest clusters, and you notice that the clusters didn't change. So the clusters include, this cluster includes point 2, 3, 5, and 6, and the blue cluster includes 1 and 4. So the new centroids will be the same. So since the algorithm did not change the new centroids, if I repeat it again and again, it will still be at the optimal point. So this is my optimal clustering based on the Lloyd's algorithm, starting from point 1 and point 4 as my initial centroids. You might want to try it again by choosing a different centroid as your initial centroids and see if the algorithm changes the results. Most probably it wouldn't, because the data is not complex, but go ahead and do a quick calculation. Also, you might want to try what if k was 3 and solve it manually by yourself to gain more experience on how to do it. With this, we end our discussion on partitioning cluster analysis. If you like the video, please hit like and subscribe and share it with others, and also add comments if there are points that you want us to explain more, or you want us to discuss, or problems that you didn't get. And thank you so much for watching. See you next time, and good luck with your data analysis.